Everyone. We will start the session now. So my name is Kedar Kulkarni. I'm an SY AI promoter at SMLRA, and welcome to day two of our Behind the Scenes of Generative AI. Today's session is going to be more about image generation using diffusion models. So your daily tools, Google's images and stable diffusion and such. As for the prerequisites, having attended yesterday's session would be a great help, but it's fine if you haven't. So no worries. In the first half of our session, I'll be covering the working of this image generation models. And in the second half, Himanshu will demonstrate how to use image generation models and make your own images. So yeah, in the first half, it is divided into the image generation, the old method that were GANs, and the new method that are the diffusion models. We will discuss briefly about the diffusion process and then in depth about how stable diffusion works, and then I'll pass it on to Himanshu. So, yeah, I think everyone here has seen what diffusion models can achieve, or at least what image generation models have achieved. For example, this image right here, I just gave it a prompt of a robotic arm drawing a landscape, and this is what the image I got was. So yeah, they are quite realistic, not quite perfect, but getting there. These are the GANs. So the older method of generating images, GANs, generative adversarial networks. I will first explain you what adversarial training is, since GANs are based upon the idea of adversarial training. Let us start with an analogy. Imagine you are given a dataset of hand-drawn numbers, and now you have to make a model that looks at these images and tells you if the given number is, say, like a 5 or a 0 or a 4, and so on. Now imagine you are trying to teach a young child. Okay, he does not know what numbers are, and you are teaching a child. So if you give the child this image, he will look at it and he will not know. So you will have to tell the child, okay, this is a 5. So he will learn from what you're prompting him. Then next you will say, give this image and tell him this is a 0, this is a 4, and so on. Now, after some training, the child will learn to distinguish between these images. But it may so happen that things like a 1 and a 7, they look quite similar. So the child might get confused between a 1 and a 7. And every time he sees these two numbers, he might like give the wrong answers because he still does not really understand the difference between 1 and 7. So as a human, what you would do is you will throw away all the rest of the numbers and you will just keep giving him the 1 and the 7 until he realizes the difference between these two. So what you did here was basically you took away all the rest of the data set and you gave him the ones and the sevens, the situation in which the child was performing the worst. This act of targeting the weakness can be looked upon as your adversary. You're basically the child's adversary. You're purposefully targeting the child's weak point so that it improves. This is what generative adversarial networks are. So what are the applications? Well, firstly, we saw one of the applications is just image generation. So this image right here, this was also generated by Stable Diffusion. Now, the other application is also playing games like chess. So if you remember AlphaGo Zero, what they did was they made the model play millions of times against itself. Since no human has the patience to play millions and billions of times, the model had to play against itself. What happened here is, say the model, the white one here, it discovered a particular strategy that is very effective for winning. Now the other blue bot here, which is also the model, it will now have to find a strategy to counter this new strategy. So basically what is happening here is the model is finding new strategy and itself is trying to defend against those strategies. So in a way, it is finding its own weaknesses and improving upon them. So this is how generative adversarial networks work. There are two components to their architecture. First is the generator itself, and there's a discriminator. You can think of them like chore and police. Okay, he is the forger. The generator is the forger. He's trying to forge fake art, and he's trying to sell it like it's a painting by Leonardo. And the discriminator is going to look at this art piece, and he's trying to tell whether this given art piece is real or fake. Now, what might happen is at the beginning, both the discriminator and the generator, they are basically idiots. They don't understand what real art or fake art looks like. So the generator is going to create some random garbage. The discriminator is going to look at that garbage and be like, well, I have no prior experience, so I don't know if this garbage is real or fake. So over time, they will learn. The discriminator will also be fed real images. So it will now have some knowledge what the real image is supposed to look like. So imagine the previous analogy where we had a data set of handwritten numbers. What will happen is the discriminator will be fed the real number first. So an 8, the image of an 8. The discriminator will go, okay, this looks realish. So it might give a 1 or it would go 0 because it still does not understand what an actual number looks like. We will, of course, give the discriminator the true label. So it will learn that this is a real 8. The next step would be the generator gets some random noise. And from this random noise, it outputs some other random noise. Now, at the beginning, it does not actually know what to do with this random noise. So it might look something like this. And the discriminator will look at this and be like, no, this just looks fake. It does not look like this. So the discriminator will go, okay, this is false. After a lot of time, what will happen is the generator will start producing images that are very close to the actual data set. So like this almost looks like an 8. So the discriminator might get fooled here, thinking that this, okay, this maybe it is real. So this is how the generator and the discriminator improve. Now, if you see, they both are basically inverse of each other. So in terms of the loss function, the discriminator's goal is basically to identify if the image is real or fake. So if it makes a correct guess, it will decrease the loss. The generator's part here is to basically maximize the loss because it wants to fool the discriminator, because it wants to create real looking copies. So this is how the generator is trained. It wants to maximize the loss and the discriminator wants to minimize the loss. So you can see how they are adversaries of each other or opponents. So this is how adversarial training works in GANs. So I'll just recap it. There's some random noise that gets fed into the generator. The generator then creates some data. There's also the real data that is the part of our data set. We will pick one at random and give it to the discriminator. And the discriminator now has to decide whether this given image is a generated image or a real image. That is it real or fake? This is how they basically force each other to improve. Like the discriminator in our case, the investigator and the forger. The investigator might learn that, okay, this type of paint was not available in the era of Leonardo da Vinci. So now the generator will be forced to source some paint that is similar to that era. So this is how they can improve upon each other. Okay, now moving on. Actually, before moving on, does anyone have any doubts? Or is the part up till here clear?
Yes,
Clear,
yes.
clear.
Mhm. Yeah, moving on to the diffusion models. These are the new method of doing things. Firstly, there are again two types of things. Like in any model, there is a forward process and there's back propagation. Similarly, here there is a forward diffusion process and there's a reverse diffusion process. So first we'll take a look at what the forward diffusion process is. What exactly happens here is, say you have a image, again, a real image of a cat. What you're going to do is keep adding some amount of noise to this. Now, what actually this noise is mathematically, it's a Gaussian noise. If anyone here knows Gaussian noise, they will realize that, say, this is time step one, this is time step two, this is time step three, and so on. So like noise one, noise two, noise three, noise four. If you want to calculate noise four, which is basically the original image plus some noise, plus some noise, plus some noise, and so on, the Gaussian function basically allows us to calculate the fourth time step directly. We don't have to calculate these intermediate time steps. So this is how it is very computationally efficient. This was the forward diffusion process. And why do we exactly add this noise? I will explain a bit later. So our forward process is you pick an image, you pick a random noise sample, you choose how much noise you want to add. So say one time step amount of noise I want to add. Then you mix these two and you will get a final image. So you can see there was a pyramid and this is some noisy pyramid. Our data set is now going to be different levels of noisy images. So it might be 3 level of noise, 14 level of noise, and so on. We will provide our model this noise amount and the noisy image itself. And for the ground truth, we will give it the noise sample itself. Our model is going to be a UNet. Himanshu in his uh, Colab notebooks, he will explain what a UNet is in short, but I'll gloss over it now. The UNet, its task is to basically predict how much noise is added in the image. So if it is given this image, for example, and it has noise amount 3, it basically has to predict what it has to subtract from this image to get back the original image. The thing about Gaussian noise is you can add or subtract it. It's a linear function. So if you just subtract some noise from this image, in theory, you should be able to get back to the original image. Now, what might happen is at the very beginning of the training, it does not know what it is supposed to subtract. So the image that you would get after subtraction probably won't look like the original image. It will look like some denoised, slightly denoised version of the image. So it will first compare with the actual noise, that is the label that we gave, and then back propagate and update the weights and so on. So yeah, the UNet will probably will like predict a noise sample and it will compare with the original noise sample and the noise amount that it got. Then it will subtract this noise from the noisy image. Okay. It will predict how much noise that image has, and it will subtract that much noise from that image. Now the output at the beginning is going to be a slightly denoised image. It is not going to be a perfect image because our UNet currently does not know how much noise it is supposed to remove. So it will get a slightly denoised image. Now we just take this and we keep repeating these steps. So like we take the noisy image, subtract the predicted noise, get a slightly less noisy image. And we do this again and again until we get an image that looks fairly similar to the original image. This is basically our loss function. How much the predicted noise is close to the actual noise. Now, why are we not comparing the images itself? It's because comparing the noise is much more computationally efficient. If you think about it, noise is a very low amount of effort compared to a very detailed image. So yeah, this is the reverse diffusion process. There's a noisy image. You keep subtracting some amount of noise in every step, and you finally get the tangible image that we had. The thing about stable diffusion is all of the things that we've seen so far were of diffusion models in general. So like your Dolly 2s or the Google Imagen, what they do is they do all of this on the image itself. Stable diffusion and what it does differently is it takes this image and it basically compresses it down to a latent space. Now, if anyone here is familiar with image compression or text compression, they would know there are formats like JPEG or PNG. So this is something similar. We are just taking the 512 by 512 image and compressing it down to a smaller space. Why is this compression possible? So like if you look at the image of a cat, you know that the cat is going to have 2 ears, 2 eyes. It is symmetric about his middle section. So like there are some symmetries and some ways that you can use to reduce the amount of information that you need to store. So the image encoder is basically going to use these tricks. It is called the manifold hypothesis in computer science. They are going to use these tricks to basically compress this image down into a latent space. Why do we need this latent space? Is because think about the 512 by 512 image. There are three channels, red, green, and blue. So that is 786,000 pixels. So like 786,000 dimensions to this one image. You want to perform all those operations that I stated before on almost 1 million dimensional image. That is a very hard task and very computationally expensive. Using the encoder, or what they formally call a VAE or a variational autoencoder, we will compress this image down to a 64 by 64 by 4 image in latent space. So this is known as the latent representation of our image in pixel space. So we converted pixel space to latent space. This is 48 times smaller. So you can see how much computational power we are basically saving here. So the variational autoencoder, what it does is, if it has an image, it will encode that image down into the latent space, and using the decoder, it will reverse back. Now, what I said before were some of the ways of compressing. If you know your compression algorithms, PNG is a lossless compression algorithm, while JPEG is a lossy compression algorithm. What that means is when you are compressing that image, some detail is going to be lost. So the variational autoencoder is no different. When you are compressing this image, some amount of detail is still going to be lost. So the decoder's job is basically to try and recover this loss of detail. So Himanshu in his collab notebook will show you the compression part at the very end of the session. Now we will just do the reverse diffusion process. What happens is we start with a random vector in this latent space. This random vector is basically noise, and we will remove noise from this step by step until we get a coherent image. If we decode every step of this, we would get something like this. It's noise at first, little less noise, then some image, and then the image becomes cleaner. But our main goal is to minimize computational expensiveness. So we won't do this for every step. We will only do this for the last step. It will look something like this. Like gradually it goes from noise into an actual image. So yeah, we will only do this for the very last step. So we start from a random tensor in the latent space. We apply our generator, stable diffusion generator, that is the UNet here. And we get a process tensor that we then decode using the variational autoencoder's decoder. And we get the pixel space image. This image we can see is it's a 512 by 512 image. Okay, a quick recap. This is our forward process. Our image is first during the training process, that is, our image is first encoded into a compressed image latent. Then the noise is added to this, and then it is forwarded to the reverse diffusion part. During the reverse diffusion part, a completely noisy latent is first subtracted, and it keeps subtracting some amount of noise until we get a final processed tensor, and this tensor is then decoded into the final image. Does anyone have any doubts here? Should I explain anything again? Okay, I'll assume that there are no doubts and move on. Okay, but when does the text prompt come into the picture? A pun. But yeah, so far we've only seen the generation part of the text to image model. We have not actually seen how the text prompt is used to condition this image generation part. So this is something that we called conditioning. Our image generator that we have seen so far, it's conditioned with the help of a text encoder. So the text prompt that we give first goes on into the text encoder and then into the image generator. It basically conditions the image generator to create a beautiful image that looks according to our text prompt. Okay, now if we are good with this diagram, small amount of detail will be added to this diagram as we go on. So just bear with me. The text encoder we use here is called a clip text encoder. It has two parts. There's the image encoder and the text encoder. Yesterday, in yesterday's session, Shubham actually explained some of the part of converting text into tokens. So that is used in the text encoder. Then the image does the unit thing, and it will then decode this into a final image. So we will go step by step again. We get the text itself from the user, the text prompt. It is then split into 77 tokens, also known as embeddings or token embeddings. These token embeddings are then passed into the unit, and then they are used to guide the reverse diffusion process into generating a processed information tensor, which after decoding, it will look something like the text prompt. So like paradise cosmic beach. So you can see there is a beach here. This is just the same thing, just that in every step of the unit, we are passing this token embeddings. We will look into it in more detail. During the training process, now before we were giving only the image. Now we are going to give it an image along with the caption of an image. So say I give it the image of a beach and I give it a caption like a beach on a sunny day or something. The clip model will use the image encoder to convert the image into the image embeddings and the text into the text embeddings. Now this part is actually quite similar to the discriminator of GANs. If you recall, the discriminator in the GAN was basically trying to check whether the generated image is fake or real. So is it similar to the actual image? So what is happening here is it is basically trying to see whether this generated image matches the text prompt or not. If it does not match, of course, we are going to give it the label that is it matching or is it not matching, but it will learn from this and then back propagate. Yeah. Does anyone have any doubts so far? Okay. Okay. So yeah, in our unit, before what we were doing is only giving it the noisy image and the amount of noise that was added in that image. And the unit had to predict how much noise it must remove from this noisy image in order to get the actual image. Now what we are doing during the text conditioning part, we are also passing in the text prompt. First, of course, we convert it into the token embeddings and then pass it because, of course, computers do not understand what text is. As Shubham explained yesterday, we first have to convert this text into tokens. So these tokens are also passed. So now our data set looks something like this. There is the time step, basically how much noise was added to the image, the noisy image itself, and the tokens, the text tokens. And for the output label, we give it the actual amount of noise that is added, and we pass it on to our unit. Now, if you recall, without the text, what was happening? The compressed image latent, the noisy image latent, it was passed on to the unit along with the amount of noise, and it was predicting how much noise was in it. So inside the unit, what is happening is this noise amount is fed into every part of the ResNet. And then it is finally predicting after some amount of steps, it is predicting the noise sample. There are actually 50 resonets in this case, in the unit. With the text, what is going to happen is, along with these two, we are also passing the token embeddings. So After every ResNet, there is going to be an attention model. If you remember from yesterday's session, when Shubham talked about transformers, there is an attention mechanism here. So if my, say, the sentence or the text prompt is a man with blue eyes wearing a red shirt, blue eyes and red shirt are going to be combined here. So the model produces something that looks like a guy with blue eyes and not with brown eyes or something. So the clubbing of these two terms, blue eyes, is called self-attention. It is done in the text encoding part itself when the tokens are created. This part is called cross attention. It is basically looking at the text prompt and then looking at the image that is being generated and then checking if the image is going according to the text prompt. Yeah. So this was the transformers. This was basically the transformer, the unit. I will explain all of that shortly again. During our training process, you give it the image itself. The image first is passed on to the encoder of our variational autoencoder. It is converted into latent representation. Then in the forward diffusion process, it is first converted into an ZT. ZT is basically a time step. So like after adding noise amount of 1, it becomes Z1, then Z2 and Z3 and so on till ZT. Now the conditioning can be done using a semantic map, text, representations, or images. So I am only going to cover the text part. The images part will be covered later during Himanshu's session. Now, all of this is passed into the clip text embedder. It is first converted into the tokens, and these tokens are now passed into the transformers. So you see the KQV here. These are basically transformers that are giving cross attention to the image that is being generated in this arrow and the text that we got in this arrow. And these are the skip connections. Again, Himanshu will show this in the detailed unit diagram. So this was our transformer. And from Z time step T, we will predict Z time step T minus 1. So we will basically predict how much one time step, like how much the image would look like after removing one time step amount of noise. And we will continue this process until we get like t minus 2, t minus 3, and so on till z. So if when we get the original latent back, we will decode it into the pixel space. So all of this is done in the latent space. This latent space part is actually what is new to stable diffusion. Dolly and all of the other image generation models, diffusion models, they only do the diffusion process and denoising unit. They do not perform this inside the latent space, so they don't have the variational autoencoders. Okay, I'll briefly just introduce you to image to image. Say you want to create like a realistic photo of a green apple. So what you can do is basically in like Microsoft Paint or something, you can just give it a rough sketch and then describe the image. So you will have to feed it two things. First, the image itself and the text prompt. Say like an green apple, tasty looking green apple photograph with 30mm camera or something. So it will output a portrait basically. All of this part is handled in a similar way to the text. It is first encoded using the variational autoencoder into a latent image and then passed on similar to the our text. That is all from my side, and I will pass it on to Himanshu now. He will explain what the collab notebooks and all do.
Hello everyone, good afternoon. I'm Himanshu Patil and I'm a AI promoter at SMLRA. I'll just share my screen, just a second. So yeah, so the models that we have seen up till now were mainly GANs and stable diffusion. So in GANs, we had the ability to make images out of images. But even if we needed a large amount of data set and a large amount of computation power for the same, we didn't have any sort of control over the generated images, right? So for example, in the first example, we can see these are the images generated by a GAN, but we do not have a control over let's say, the hair color or the color of the eyes or the skin color of the person. This was later then solved by stable diffusion with the help of a text prompt, where we gave it a prompt of a man with, let's say, brown eyes, and it would create a man with brown eyes. So what if we had even a greater level of control over the image? What if we wanted to make the image out of something of our own, like for example, our own face? So this is achieved with the help of a control net. So what is a control net? To understand control net first, you have to understand from the previous example from stable diffusion to understand what a unit is. So unit, the model actually looks quite similar to that of a U. So in the unit, what happens is that we take the original image and we have a downsampling. We downsample it down to to a smaller representation. Then we later upsample it and we get the output. What Why this is important is because we already did have these models, but in unit we have something called a skip connection, where essentially every single time we downsample it, we pass the latent representation, or we save the latent representation and pass it on to a upsampling block later on. This allows us to retain uh, the similarity of the image uh, from the provided image. So once you understood the unit, you can see this is the ControlNet model that was in the original ControlNet paper. So what is a ControlNet? ControlNet is essentially the stable diffusion model plus an external model. So this is the original stable diffusion model on the left-hand side, which takes in the normal inputs, that is the text embedding from the user, and generates the images based on the given prompt. What The second model, that is the external model that is over here, is the same as that of the downsampling part of the stable diffusion model over here. That is, for example, it's over here. So what does this do is that it downsamples the text as well as the image. The second model, external model, we provide the image as well as the text, and it downsamples it down to a tensor. Now, with every single step in this second external model, we pass on this tensor and literally add it to the actual stable diffusion at every single step. This allows us to have a greater amount of control over the generate image, and we have the ability to use our own images in order to make something more beautiful. So why is this architecture very important? Up till the paper, we can see that the models that were created up till now were always trained from scratch. We created the model, we trained from scratch. We use like large amount of computation powers. So in this scenario, what this allows us to do is that we retain the original stable diffusion model. So the trained weights of the original stable diffusion are retained in the original model, and we are just using the external network to sort of to make the to have more specification over the generated images. So in this notebook, we'll kind of demonstrate how the ControlNet works and what are the applications of ControlNet. So first we'll install the dependencies. The first one being diffusers containing the ControlNet stable diffusion ControlNet pipeline, the OpenCV, and the ControlNet aux. The ControlNet aux contains all the helper function that may be required for the image generation during. Yeah. Then we'll import all the libraries required. And let's say we want to create we want to use a famous image as an input. So we'll use this lady in the painting. Don't remember the name of the image, so that right? We'll use this image and we'll convert it into something of our own customization. So first of all, now the step ControlNet model that was in the original paper has many models with different types of application. We can use CAN images. You have different like depth estimation. You have from sketches. So for different types of input, it has different models. So we'll convert this image into a CAN image. CAN image is nothing but just an edge detection program, which just detects the edges, and we can convert it into a black and white image as shown. So then we load in the ControlNet pre-trained pipeline for made for CAN images, and let's say we want to, and let's say we want to make something interesting, right? So this image looks quite from like medieval times, and we want to make it into something more modern. So what I came up with as the best prompt for this purpose was to convert it into an anime image. So with the results, we can see the image is converted into a completely different art style compared to that of the first image. And the second image we have replaced the face from the image to a Taylor Swift. So you can see the image actually is replaced, the face is actually replaced by that of a Taylor Swift. So for comparison, you can see the original image, which looks quite, in fact, old and medieval, but it can be replaced with something of a modern art style. Now, the ControlNet app can be applied not only to CAN images, but also to pose images. So let's say you have a pose that you want. So let's say you want to create your own pose and you want to have a superhero with the respective pose. So you'll install the same dependencies as before, and these are the few yoga images that I found on the internet that we are going to use for this purpose. Now, the ControlNet Aux library that I mentioned before, we are going to use what is called as an open pose detector. That is nothing but a pretend model that detects the poses from the actual human being. So as you can see, we get the image, we get an image with the poses or every single joint from the human body, and then we'll pass it on to the ControlNet pre-trained open post pipeline. So we can see, let's say we want to create it into a superhero, right? Everyone wants to be a superhero. So we'll make these poses into a superhero with the same poses. So with the generated images, we can see that the first one is like it looks quite good, right? It is just so beautiful. There's a city behind. We can see that the pose is actually same as that of the given pose, and the second one is looks quite cool, right? So you can see that the poses in the images are the same as that of the given poses from the yoga picture. So not only can ControlNet be used on poses and can images, but many other. For example, we want who here is great at drawing. Mainly, so say you want to convert your drawing into something that we actually envision. So you can also convert that into an actual drawing from that uh, from scribbles. We can use step from the same ControlNet pipeline. We can uh, give an input of a sketch of the dog that doesn't look like a dog, but yes, to be converted into actual dog. So all these applications, if you want to try, can be viewed on the original Stable Diffusion's website. You can just use a normal prompt to image in this case, or you can actually use a ControlNet, and you can see that we have very different options for different types of images like Canny, HED, Scribble interactive poses, even depth estimation models or segmentation. So you can use them. Now, all these applications that we have seen up till now are all like fun related. Image generation is quite good, but it is not that useful, right? So what is a real life application of stable diffusion? So the real life application of stable diffusion is it can be used for compression. So in case of compression, we can see sorry. So in case of compression, we can use the, as Kedar explained, the latent representation is quite small compared to that of the original image, right? So you can, what if we could save that latent representation in a format and re-import it and then use the uh, stable diffusion pipeline to reconstruct the image from the latent representation. So first, as all cases, we'll install all the dependencies. It is patterns, OpenCV, diffusers, and transformers. Now we uh, for running this notebook, you'll require a Hugging Face token login. So you'll require a Hugging Face ID, of course, and you can get the token. The instructions are mentioned over here. So now up till now, what we did is that we used the stable diffusion pipeline and imported the entire pipeline at one single time, as in all both of the previous cases. We imported the entire pipeline at the same time, but we need to grab the latent representation from between the pipeline, right? So you'll have to set up the pipeline individually. So we'll first set up the variation autoencoder, the unit model, the scheduler, the text encoder, the clip text model encoder, and the tokenizer. So once we have set up all these pipeline, we'll we'll define some helper methods. So what are these helper methods? Helper methods are nothing but the methods that we are going to use in the main method to generate the compressed image. The first one is a make latents. So make latents is nothing but to convert the image with the help of an variation autoencoder to a latent representation. Similarly, we have a vice versa of the uh, same function, that is make image, that converts the latent representation to a image with the help of the variation autoencoder decoder part. The third function, that is a resize function, is quite self-explanatory. We essentially resize the function to 512 by 512 pixel image. Now the fourth function, that is the quantize function, is quite important because if the colors of the image are continuous, we may require a large amount of computation as well as a large amount of space to save the image, right? So what does this quantize function do is that it scans the image for continuous colors. For example, we have a blue, we have a darker blue, and even a more darker shade of blue. So what does this do is that it grabs all these pixels having the same color and takes the mean of these colors and puts in and replaces the colors with the same color. And quantize does the vice versa and converts the image, or the sorry latent, into a array format that is to be passed on to the generator model. The last function is the denoise function that will be using a unit architecture in order to predict the amount of noise in the image. Now you'll ask, but we are not actually adding certain amount. We are not actually adding noise, right? But what happens is in this image is that once you have performed all these functions over the latent space, the image will actually get quite noisy, and we'll have to undo that with the help of a unit. We are not adding extra amount of noise in this case. Okay. So in the main function, we'll first get the ground truth image. So this is a beautiful image of a cityscape, which we can see has the space of about 2,09,874 bytes, right? So what happens after one round trip from a variation autoencoder? So one round trip from a variation autoencoder means it is first changed into uh, a latent representation, and then we are reversing back to the actual image. So in this case, we can see the image is quite distorted. Excuse me. So you can see that the image is quite distorted, and the details from the original image are completely lost. For example, if you see the building over here and compared to the building down here, we can see that the straight lines from the original image have been like completely destroyed. We can see that this is quite blurry enough. We can't make out any kind of details. So what happened? So we can use the denoise function above that we have defined above, the denoise function, in order to remove the certain amount of noise and get it back to at least um, an acceptable state. Let's say for so the after denoisation, we can see that the image generated is quite better compared to the second image. We can make out most of the details, but even though this is the case, the disadvantage for this is that yes, the information from the image is lost. The we lose important information from the image, and the image in smaller part gets quite blurry compared to the original image. But on the brighter side, we can see that the amount of space that we required first, that is 2,09,874 bytes, is reduced to 30,478 bytes. That is, which is actually quite a huge amount of compression, and which can save us quite a large amount of space. This may be used. This can be done in let's say in future implementations where the stable diffusion may be able to reconstruct the entire image directly from the given latent representation. Now also we are also with the, after this we save the latent representation in a .webp format, and which can be later reused with the help of the quantized and unquantized functions and the denoise function to recreate the origin image. So any doubts up till now? The compression. So I guess that will be all for this session. Yeah. You can find all these notebooks on SMLRA's GitHub page uh, as well as the recording for this session will be posted on YouTube. So you can check that out. And thank you guys for attending and staying till the end.
Can you share this notebook on WhatsApp?
The notebook will be is on the GitHub page. We'll share the link for the GitHub and the recording on WhatsApp. So you can check that out. Any other questions?
Or I will say just explore the Stable Diffusion website. The website itself has many, like it has a great UI if you want to do all of these things. Or if you just want to see the code, of course, you can just check out our GitHub. Yeah.
Any other questions? Okay, so we'll end this session now. Thank you everyone for joining.